and welcome. My name is Zachary Wilkerson, and today I will be presenting to you my work, Scale Transform Signal Processing for Reducing the Effects of Rain on SSTDR Signals. We'll begin by acknowledging some of my colleagues. First, at the University of Florida, Ayabami Adun, Cody Laflemme, as well as Dr. Joel Harley. In addition to my colleagues at the University of Utah, Dr. Michael Scarpulla and Dr. Cynthia Furse. We begin by discussing the motivation of our research. We are looking to detect and locate electrical faults in photovoltaic systems. As you can imagine, looking at the picture shown here, when working with a solar farm with many panels connected, we want to immediately identify any and all faults in order to keep our systems up and running. Typical faults that we run into working with these panels are disconnects, perhaps from animals roaming around and tripping on wires, ground faults, which can occur from frayed cables, arc faults, which can be very serious and cause electrical fires. These need to be identified immediately and resolved, as well as shade faults, where our panels are being covered. In order to detect and locate these faults, we turn to a method called spread spectrum time domain reflectometry, or SSTDR. Now, SSTDR is very similar to ultrasonic testing, where we're going to send a high frequency electrical signal, here the incident pulse, down our transmission line, and we're going to receive reflections whenever we hit any impedance discontinuities. With these two signals, the incident signal and the reflected signal, we're going to do a cross correlation. And that resulting signal that we have is the typical SSTDR signal that we work with. Now, the time delay between my incident and my reflected signal is going to represent the distance to the fault in question, and the amplitude is going to give us the magnitude of that fault. Shown a little bit better is in this image. Again, we've got our incident and our reflected signal, and the bottom is the traditional SSTDR signal, where here we notice an open circuit. Now, some of these have characteristic features, such as the open circuit has a large positive peak, and a short circuit has a large negative peak. If we have a matched impedance, we typically see a relatively neutral region of our signal. And if we see any mismatched impedances, we'll see this mixture of some of the characteristics that we've already looked at. Now, in order to locate these faults, we do something called baseline subtraction. So shown here, in the top figure, we have the baseline as well as samples of signals that we've taken. The baseline is in blue. The signals that are constantly changing are the signals in orange. Now, we will take the baseline and the signal in question. We will do baseline subtraction, so we will subtract one signal from the other, and we get the resulting figure in the middle. The location, as we discussed, of any major peaks or dips corresponds to the location of the fault, and the magnitude gives us information about what type of fault occurred. On the bottom, we simply show the correlation between the two signals. A very high correlation close to 1 typically corresponds to some daylight, whereas that moderate dip that you see corresponds to nighttime. Any larger dip, such as the 3 or 4 that you can see in this problem, correspond to actual faults. One coming up right now, as you can see. So baseline subtraction is our go-to when we're talking about detecting and locating these faults. Now, baseline subtraction is great, but we do run into some issues when working with baseline subtraction. For example, our data can change due to environmental factors. When we see differences in illumination, temperature, humidity, and rain, and particularly moisture, our signals start to change. So you can imagine if we input an SSTDR signal shown here on the left, we might get a response one day that looks like the middle signal, But then another day, we might get a totally different signal. And so this leads us to the question, how am I going to be able to perform a baseline subtraction on data that's constantly changing? In this presentation, we will be focusing on the effects of rain and with that moisture on our SSTDR signal. What we've noticed is that moisture from rain changes the relative permittivity of the cable that we're working with, and consequently leads to a change in the velocity of propagation, or the VOP, of the SSTDR signal. Now this change of VOP is going to stretch our SSTDR signal and therefore shift the peaks out of place, leading to inaccurate fault detection when using our baseline subtraction. This image quite clearly shows it, where the black is an ideal condition SSTDR signal. And we've got 3 rain samples shown in the red, the yellow, and the purple. As you can see, when moving from the black to the other signals, now our solution to this issue is the scale transform. The scale transform is a variant of the Mellon transform, which has many different stretch invariant properties. What this means is that a stretch in our time domain is going to correspond to a delay in the Mellon domain. Specifically, we use a computationally efficient approach known as the scale invariant correlation iterative scale transform, also known as SICEAA, where a scale factor estimate is produced by a maximization of a scale cross-correlation function. We then compensate for the effects of rain in our SSTDR signal, which we saw as the stretching in the time domain, by stretching our distorted rain signal by the inverse of our optimal scale factor estimate. We can see this in the 2 images shown below. So on the left, we see the baseline signal in red, and we see the original rain signal that we're going to be working with in black. Now, what we want to do is we want to take this rain sample in black and ideally shift it back to match up with our baseline red signal. As you can see, some of the peaks have already been shifted out of place, such as the first 2 over here, as well as this peak and this black peak here. And so what we've done using our scale transform is we've identified a scale factor of 1.2246. And so what we will do is take our rain sample, stretch it back using this scale factor, and we get the figure on the right, which shows that the baseline and the reconstructed rain signal now match a lot better in terms of their peaks. What this means for us is that we're able to take this noisy rain signal that's been distorted and bring it back into a form where we don't see any effects from rain. That way, we can perform baseline subtraction on this new reconstructed signal. Now we'll look at some of the experiments we've done. So first, we start off with a single panel with no faults under rainy conditions. We'll then move on to 5 panel setup with no faults in ideal sunny conditions with no rain. So for the first panel under these rainy conditions, the left graph shows in black the original data that we've taken. Now, when we do a correlation between the SSTDR signals we have and a baseline SSTDR signal, we get this graph. As you can see, rain starts to pick up about halfway through the samples we take, and our correlation coefficients dip drastically. Now, after applying the scale transform, we get the graph in red, which shows our correlation coefficients are being raised up to appropriate levels so that we can now use baseline subtraction on all of our samples and not just the samples where we're getting good results in the beginning. Also displayed in the figure on the right is the scale factor versus our samples. As you can see in the beginning, our scale factor is roughly about 1, which means that our signal is not going to be changing at all. And this is as we would expect because we don't have any of those rainy conditions in the beginning. But But once we reach the middle of our samples and we match that up with the drop in our correlation coefficients, we see the scale factor jumps up and we've got some fluctuations as we start to match the signal to our baseline. Now we move on to the 5-panel data. Remember, for the 5 panels, we're working with ideal conditions. So this is day and night, normal sun, no rain conditions, anything like that. Again, we've got our 2 figures. The left figure shows our correlation coefficients with the baseline and the signals in question. What we see as we move from the black, which is the original correlation, and then the red, which is the correlation after we performed our scale transform, we're able to reduce a lot of the noise that's coming from our signals. So as you look up at the top green dotted lines, we see a lot of fluctuation in the black, right? Dips and coming back up. When we perform the scale transform, we get nice, smooth lines up top. We see very similar thing happening at the bottom, where the dotted green presents our boundary and the black correlation coefficients that were very rigid become a lot smoother after we performed our scale transform. On the right, just as we've done in the past, we show the scale factors that correspond to the samples that we showed from the left graph. And as you can see, the scale factors are pretty much consistent across the board. So when we're talking about those daytime signals, most of them are roughly around 1. When we move to those nighttime samples, we see that the scale factor is about 8.82. Now, what this data means is that our scale transform is actually able to reduce noise that's occurring even during our ideal conditions. This is promising because if it can reduce noise that's occurring from ideal conditions, when we switch to rainy conditions, we expect our scale transform to not only adjust for the traditional noise that's occurring in our ideal conditions, but also add in some adjustments for the rainy conditions, such as it did in the 1-panel case. With that being said, we'd like to do a summary of first our current work, which is that we've used the scale transform to mitigate the stretching of our SSTDR signal due to the effects of moisture and rain. We showed that in the 1-panel setup where we were dealing with rainy conditions. However, we were not able to show that in the 5-panel setup as we do not have any data as of right now for that rainy conditions. For future work, we'd like to apply our scale transform process on data with varying types and number of faults. Remember, in the 1-panel and 5-panel data, neither of those had any faults occurring in them. We were simply showing a proof of concept that we can mitigate the stretching in the time domain that was occurring from our rain. Now, with that, we may also want to investigate the use of the scale transform with other environmental factors, such as, like we talked about, temperature, humidity, illumination, things like that. I'd also like to state that, as a disclosure, Dr. Cynthia First is a co-founder of LimeWire Innovation Incorporated, which is commercializing SSTDR technology, and therefore has a financial conflict of interest with this company. I'd also like to note that this material is based upon work supported by the U.S. Department of Energy's Office of Energy Efficiency and Renewable Energy, EERE, under Solar Energy Technologies Office Agreement Number DEEE0008169. I'd like to thank you for coming to my talk. If you have any questions, please feel free to email me. My email is zwilkerson@ufl.edu. Again, zwilkerson@ufl.edu. Thank you for your time. I hope you enjoyed.